The law of conservation of energy states that energy is conserved over time. This means that um, energy is neither is created nor destroyed. Rather, it is transformed from one form to another. So in this video that shown right here, I'm doing the part where having needles at the bottom of the cup pop the balloon, which causes the balloon to blow out the candle. Now, in this scene, as you can see, the weight hits the balloon and it pops, causing the balloon to blow out the candle. Now, in this sense, the cup at first has potential energy when it is up above the floor about 1 meter. And as soon as the weight and the golf ball go inside the cup, it brings the cup down, which causes it to have kinetic energy, and the kinetic energy of the cup hits the balloon, which causes it to pop. Now, in the balloon, there is air that is trapped inside of it, and in this balloon, the air has potential energy, and when the balloon is popped, that potential energy is converted into kinetic energy because it escapes the uh, balloon, and this kinetic energy of the air causes it to blow out the candle. So now for our calculation part, we need to figure out the work done by the balloon. But before we solve that, we need to figure out the pressure of the balloon. So the pressure is recorded in kilopascals, and the equation is PV equals nRT. And where P is the pressure, N is the density, R is the universal gas constant, which is in joules per kmol. The T is equal to the room temperature, which is measured in Kelvin, and V is equal to the molar mass of air. So now using the equation, we figure out that the pressure is equal to the density of the air, which using Google I found it to be 1.225 kilograms per meter cube, times the universal gas constant, which was just given to me, which is 8.31 joules per kmol, and times the room temperature in Kelvin, which the room temperature in degrees Celsius is about 23, and converting that to Kelvin is about 296.15. And that divided by the molar mass of air. The molar mass of air is 28.97 grams per mole. Converting that into kilograms per mole becomes 0.02897 kilograms per mole. And calculating all that, we get 104,063.961 for the pressure, and which is recorded in kilopascals. And using sig figs, we get about 104,000 kilopascals. Next, after we find the pressure, we have to figure out the force, which is basically the work done. And to do that, we need to multiply the area of the balloon times the pressure. Now, the the pressure we already solved, and now we need to find the area of the balloon. So using the measuring tape, I found that the circumference of the balloon is 90 centimeters. And using the formula for circumference, we find the radius to be about 14.3 centimeters, because the formula for the circumference is 2 pi r. So you divide 90 by 2 and divide it by 3.14, and you get 14.3. Now that we've found the radius of the balloon, we can now use that to find the surface area of the balloon. Now, the surface area of the balloon, you use the formula 4 pi r squared, and we convert the radius of 14.3 centimeters to 0.143 because the SI unit for distance is meters. So when you multiply that, you get about 0.25683, and then you plug that into the force equation, where you got 104 million times 0.25683. The reason why this becomes larger is because we converted this to kilopascals to pascals. And to do that, you need to multiply your answer by 1,000, adding 3 more zeros from 104,000 to 104 million. The force becomes 26,711,301.76. 3 sig figs becomes the force is equal to 26,700,000 pascals per meter. Now talking about the weaknesses of this part of the Rube Goldberg machine is the fact that we use the formula for the surface area of a sphere, but a balloon is not a complete sphere. As you can see, it is slightly oval shaped and it kind of caves in towards the point of it, and this affects our results because this is obviously would have a different surface area than a sphere would. Another weakness of this part is the fact that we had to search up the density and molar mass of air, and quite possibly the answers that we searched up could be wrong or not necessarily accurate. For the next part that I had to do was the part where the marble hit the golf ball. And as you can see in this video, but you can see that the marble hit the golf ball. Originally, this was supposed to be the markers hitting the marble, and which hit the golf ball, but that part took too long to set up, and we did not have time to do that. So instead, we just had the marble being pushed by my hand. So for my calculation, I'm going to figure out the gravitational potential energy of this marble right now. So for the gravitational potential energy of the marble, we have to use the formula EP equals mgh, where the gravitational potential energy is EP and m is equal to the mass of the marble, g is equal to the acceleration of gravity, and h is equal to the height of the marble. So the mass of the marble was 20 grams. Converted to the SI unit for weight, it becomes 0.020 kilograms. The acceleration of gravity is 9.81, and the height of the marble was 7.5 centimeters. Convert that to meters, and you get 0.075 meters. And when you multiply all those numbers together, you get 0.014715. And using 3 sig figs, the gravitational potential energy is 0.0147 joules. Calculating the potential energy, we're going to calculate the kinetic energy of the marble. So the kinetic energy of the marble we're going to calculate from the ball moving and to the point right before it hits the golf ball. So using PhotoGate, which is not shown in this video, but we took a video after this. We calculated that the velocity of the marble was 0.541 meters per second. So using the formula for the kinetic energy, which is 1/2 mv squared, where m is equal to the mass, and v is equal to the velocity, we convert the 20 grams to 0.020 kilograms, multiply by 0.541, multiply all of that by 1/2, and we get 0.0029261. And using 3 sig figs, we get the kinetic energy to be 0.00293 joules. Weaknesses of the calculations in this part of the video were that we calculated the velocity of the marble based on how hard I pushed the marble. Now, this is a weakness because in our Rube Goldberg machine, the marble was actually pushed by a marker. But instead, this time it was pushed by my hand, which could affect the velocity of the marble depending on how hard I pushed the marble with my hand. And also, it was hard to get an accurate velocity for the marble using the photo gate because each time that I would push it, I would push the marble. Each time I pushed the marble, it had a different velocity depending on how much force I put on the ball. So that was another weakness in the calculation for this part.